All right, now what about classical? What requirement must be met in order to compute probabilities using the classical method? This requires equally likely outcomes. And how do we compute the probabilities using the classical method? So the probability of the event E is equal to, now this one's equal, not approximately equal, the number of ways E can occur, all divided by the number of possible outcomes. This can be written as M divided by N. Let's look at an example. A pair of fair dice is rolled. Fair die are die where each outcome is equally likely. So we're looking here at the sum. So compute the probability of rolling a sum of 7. So let's circle all the dice with a sum of 7. If we go back up to our definition, what are the number of ways E can occur? 6 times. And what's the total number of possible outcomes? There are 36 possible outcomes here. This reduces to 1 over 6. And then compute the probability of rolling snake eyes. Snake eyes means a 1 and a 1. So we have 1 out of 36 chance. So we just saw that the classical probability of rolling a 7 is 0.167, or 1/6. Suppose a pit boss at a casino rolls a pair of die 100 times and obtains 15 sevens. From this empirical evidence, because we're doing trials, we would assume the probability of rolling a 7 as 0.15. If the dice are fair, we would expect the relative frequency of 7s to get closer to 0.167 as the number of rolls of the dice increases. So kind of like when we did the coin flips, as the trials increase, so these are the empirical, as they increase, we're going to get closer and closer to the classical, which is going to be your 0.5. So as the number of trials of an experiment increase, how does the empirical probability of an event occurring compare to the classical probability of that event occurring? The empirical probability will get closer to the classical probability as the number of trials of the experiment increases. So the more and more times you do the empirical probability or these trials, the more trials you have, the closer you are going to get to the classical probability. So Sophia has 3 tickets to a concert, but Yolanda, Michael, Kevin, Marissa all want to go to the concert with her. To be fair, Sophia wants to randomly select the 2 people who go with her. Okay, in this instance, order does not matter, right? If we pick Yolanda and Kevin, it doesn't matter if it's Yolanda and Kevin or Kevin and Yolanda. So order does not matter in this example. And I'm just going to label each person a number. So the first step is to determine the sample space. So we could have Yolanda and Michael, Yolanda and Kevin, or Yolanda and Marissa. Okay, what if Yolanda didn't go? We could have Michael and Kevin, Michael and Marissa, and then we could have Kevin and Marissa as an option. So compute the probability of event Michael and Kevin, so 2 and 3, attend the concert. So we have 1 over how many possible options are there? 6. So compute and interpret the probability of the event Marissa attending the concert. Marissa doesn't care who she goes with as long as she goes. So we're going to circle all the groups of 4 we see. That's 3 out of 6, which is 1/2. So Marissa has a 50% chance of going. So if we interpret that, I kind of just did. Marissa has a 50% chance on attending the concert. Let's look at another example. Suppose that a survey asked 500 families with 3 children to disclose the gender of their children and found that 180 of the families had 2 boys and 1 girl. Estimate the probability of having 2 boys and 1 girl in a 3-child family using the empirical method. So the empirical method again refers to trials. So how many had 2 boys and 1 girl? 180 out of the total, which was 500. So it's approximately equal to 0.36. Now compute and interpret the probability of having 2 boys and 1 girl in a 3-child family. Okay, so we have 3 children. What are the options of the gender? So now the order matters. So we could say the first child was a boy, second child was a boy, third child was a boy. We could say boy, boy, girl could have been an option. Boy, girl, boy could have been an option. Girl, boy, boy. Boy, girl, girl. Girl, boy, girl. Girl, girl, boy. Or girl, girl, girl. So this is a classical method. Okay. So how many ways can 2 boys and 1 girl occur? 2 boys, 1 girl. So I'm seeing 3 out of the total, which is 8. So this is 0.375. So the more times we did this 500 trials, if we did this maybe 1,000, this empirical probability is going to get closer to the classical. Empirical probabilities and classical probabilities often differ in value, but as the number of repetitions of a probability experiment increases, the empirical probability should get closer to the classical probability according to the law of large numbers. So we've already discussed this, but I'm just reiterating it. However, it is possible that 2 probabilities differ because having a boy and having a girl are not equally likely. Maybe the probability of having a boy is 0.505. The probability of having a girl is 0.495. If this is the case, then the empirical probability will not get closer to the classical probability because the events boy and girl are not equally likely. Because if you remember, the requirement for classical method was to have equally likely outcomes. So we covered empirical and classical probability. Now we will go on to the final third probability, which is subjective probability. This is determined based on personal judgment. So why are subjective probabilities used? Sometimes this is the only method of assigning likelihood of an outcome. Let's look at an example below of a scenario. A financial reporter may ask an economist about the likelihood of the economy failing into a recession next year. Again, we cannot conduct an experiment n times to find a relative frequency. The economist must use knowledge of the current conditions of the economy and make an educated guess about the likelihood of the recession. So this is when you would use subjective probability, when it is impossible to do experiments. Let me know if you have any questions. Please email me or post to the discussion board. Thank you.